On the basis of the type of forces holding the constituent particles together, crystalline solids are broadly classified into molecular solids, ionic solids, metallic solids, and covalent or network solids. Let us begin our discussion with molecular solids. The constituent particles in these type of solids are either atoms or molecules. The atoms or molecules are held together by weak forces of attraction. Further, on the basis of the nature of the intermolecular forces of attraction, molecular solids are divided further into non-polar molecular solids, polar molecular solids, and hydrogen-bonded molecular solids. Let's discuss each in turn. In non-polar molecular solids, the constituent particles are either atoms or molecules. The atoms or molecules in these solids are held together by weak dispersion or London forces. As a consequence, these molecules have low melting and boiling points. Hence, most of them are liquids or gases at room temperature and normal atmospheric pressure. For the same reason, they are soft. As the electrons remain localized to particular atoms or bonds, these are non-conductors of electricity. On the basis of the type of forces holding the constituent particles together, crystalline solids are broadly classified into molecular solids, ionic solids, metallic solids, and covalent or network solids. Let us begin our discussion with molecular solids. The constituent particles in these type of solids are either atoms or molecules. The atoms or molecules are held together by weak forces of attraction. Further, on the basis of the nature of the intermolecular forces of attraction, molecular solids are divided further into non-polar molecular solids, polar molecular solids, and hydrogen-bonded molecular solids. Let's discuss each in turn. In non-polar molecular solids, the constituent particles are either atoms or molecules. The atoms or molecules in these solids are held together by weak dispersion or London forces. As a consequence, these molecules have low melting and boiling points. Hence, most of them are liquids or gases at room temperature and normal atmospheric pressure. For the same reason, they are soft. As the electrons remain localized to particular atoms or bonds, these are non-conductors of electricity. In polar molecular solids, the constituent particles, molecules, are formed by polar covalent bonds. Solid sulfur dioxide and solid hydrochloric acid are some polar molecular solids. The molecules in polar molecular solids are held together by relatively stronger dipole-dipole interactions. As a consequence, these solids have relatively high melting and boiling points. However, these are usually gases or liquids at room temperature and normal atmospheric pressure. Like non-polar molecular solids, these are also soft and non-conductors of electricity. In hydrogen-bonded molecular solids, like polar molecular solids, the constituent particles, molecules, are formed by polar covalent bonds. However, the bonded atoms in these molecules are essentially hydrogen and a highly electronegative atom, such as fluorine, oxygen, or nitrogen. Ice and solid hydrofluoric acid are two examples of hydrogen-bonded molecular solids. The molecules in these solids are held together by strong forces of attraction called hydrogen bonds. As a consequence, these solids have high melting points among the three types of molecular solids. Like the other two types of molecular solids, these solids are also non-conductors of electricity. At room temperature and normal atmospheric pressure, these are either soft solids or highly volatile liquids. The other type of crystalline solids is ionic solids. These solids have the ions as their constituent particles. The Coulombic or electrostatic forces of attraction hold the ions, cations, and anions together in the crystal. These cations and anions arrange regularly in three-dimensional space to form ionic solids such as sodium chloride, cesium chloride, and zinc sulfide. These solids have high melting and boiling points. This is attributed to the strong electrostatic forces of attraction. As a result, these solids are also hard but brittle. As the ions are in fixed positions, they are non-conductors of electricity in solid state. However, they are good conductors of electricity in fused or in their aqueous solutions. This stems from the fact that the ions acquire freedom of movement in their fused or aqueous solutions. You know that on the basis of the type of force that holds the constituent particles together, crystalline solids are broadly classified into molecular solids, ionic solids, metallic solids, and covalent or network solids. Let us begin our discussion with metallic solids. In metallic solids, the metal atoms, such as copper, iron, silver, and magnesium, lose their valence electrons to the crystal as a whole. These solids are merely a collection of positive ions surrounded by and held together by a sea of electrons. Hence, the constituent particles in a metallic solid are positive ions in a sea of delocalized electrons. The electrostatic forces of attraction between the positive ions and the electron cloud constitute the metallic bonding, which holds the positive ions together. These electrons are not localized on any atom, but rather delocalized uniformly over the entire crystal. These free and mobile electrons make metallic solids good conductors of electricity and heat. The electrons flow through a network of positive ions when an electric field is applied. Similarly, when heat is supplied to one corner of a metallic solid, the free electrons spread the thermal energy evenly throughout the solid. The presence of free electrons also accounts for the luster and color in some cases. Metals are highly malleable and ductile. Metallic solids have fairly high melting and boiling points. The other type of crystalline solids is covalent or network solids. The constituent particles in these solids are atoms. These atoms are held together in large networks by covalent bonds. This interlocking network of covalent bonds extends throughout the crystal in all directions. Hence, covalent solids are also called network solids. They are also termed as giant molecules. Diamond, graphite, and quartz are some network solids. As the atoms are held by strong covalent bonds, these solids are very hard and possess very high melting points. These solids are non-conductors of electricity except for graphite. In diamond, each carbon atom is bonded tetrahedrally to 4 other carbon atoms. Thus, a regular tetrahedral arrangement of carbon atoms bonded to one another in a 3-dimensional manner forms a network, resulting in a rigid giant molecule. Note that diamond is the hardest substance known and has a melting point of 3550 degrees Celsius. On the other hand, graphite is an exceptionally good conductor of electricity and is extremely soft. In graphite, each carbon atom is bonded to 3 other carbon atoms, resulting in hexagonal rings, which, when repeated throughout a plane, form sheets or layers. In its layered structure, the layers of hexagonal rings are arranged parallel to each other, as shown here. These layers are held together by weak van der Waals forces of attraction. The layers can slide over one another when impurities are present between them. On account of this, graphite is soft and can be used as a solid lubricant. As each carbon atom in graphite is bonded to only 3 other neighboring carbon atoms, the 4th valence electron is free to move about in different layers. Thus, the free mobile electrons account for the exceptional electrical conductivity in graphite. Crystalline solids have an orderly arrangement of their constituent particles in 3 dimensions. The positions of these particles in a crystal relative to one another are usually shown by points. An arrangement of an infinite set of these points is called a crystal lattice. Thus, a crystal lattice is a regular arrangement of the constituent atoms, ions, or molecules in 3-dimensional space. Sometimes, A crystal lattice, also called a space lattice or simply a lattice. There are only 14 possible three-dimensional lattices. And are called Bravais lattices, after Auguste Bravais, a French mathematician who first described them. Now let's look at the characteristics of a crystal lattice. Each point in a lattice is called a lattice point or lattice site. Each point in a crystal lattice represents one constituent particle, which may be an atom, a molecule, or an ion. Lattice points are joined by straight lines to bring out the geometry of the lattice. A crystal lattice can be subdivided into several cells, known as unit cells. Thus, a unit cell can be defined as the smallest portion of a crystal lattice, which, when repeated in different directions, generates the entire lattice. A unit cell represents the shape of the entire crystal. In fact, a crystal may consist of an infinite number of unit cells. A unit cell is characterized by distances A, B, and C along three edges, and angles alpha, beta, and gamma between pairs of edges. Alpha is the angle between edges B and C. Beta is the angle between edges C and A, while gamma is the angle between edges A and B, as shown here. Edges A, B, and C may or may not be perpendicular to each other.